Welcome everyone, and before we start as usual, let me spend just 30 seconds to make sure that my setup is correct today. Okay, sorry for the slight delay because I was struggling to get all my cables in order. Okay, so it seems that you can see me, you can hear me, so welcome to this very special episode of Iron Beetle. So what is Iron Beetle? Iron Beetle is a show where we, during the last almost 50 episodes, looked at this incredible database, TagBeetle, really deep. We tried to understand, from the first byte that arrives from the network to the last byte that gets down to disk, how this whole thing works. How you could implement a distributed database which runs on 6 replicas, which implements consensus, which is resilient not only to network faults, but also to disk faults. So it is resilient to disk just returning garbage, while at the same time, doing this all in a very low language like Zeek, without doing any kind of memory allocations. So it took us, as I've said, almost half 100 episodes, and the last few of them, about compactions, were pretty rough. I should say it was complicated, but I think at this point we are done. This doesn't mean that Iron Beetle ends here. For two reasons. Well, first of all, there is a ton of stuff which we haven't covered, which is kind of outside of this happy loop, but which we still need to learn about. Stuff like client sessions or the sync protocol. Audio is somewhat distorted. Okay, let me try to look at this. Okay. Well, I am supposed to be speaking through the right microphone. Not sure what's up here. Yeah, the reason for the delay is I was trying to improve my audio setup. In the end, I failed and tried to fall back to the old setup, but at that point, old setup wasn't working. So this episode is important, but I effed up the audio, but hopefully it will be bearable. Okay. Yeah, so the first reason is just a lot of things we have to cover. The second reason is that okay, gain is low, so let me try to make it just a little bit higher. Okay. The second reason why we are not done here yet is, while we were spending this 50 episodes, 50 weeks to cover TagBeetle, while I was doing Twitch streaming, the rest of the team weren't asleep. Okay, so let me try to fix the audio just a second, because okay, I hate this. I hate when it is the most important episode in a while, and my audio is worse than usual. Okay, so how about this? So hopefully, okay. So I think this is the best what I can do with my audio without spending even more time. On this, but okay, let me think. I could reduce this to this. Okay. Yeah, sorry about that. So yeah, the second reason is the rest of the team was sleeping. They implemented a ton of features. So we have things like queries. We have things like multi-version binaries. We have things like better dependency for accounts, and we need to cover all that. So we'll get to that. But today, in this very special episode, what we'll actually do is that we'll do a grand recap of everything we've covered so far. I'm not sure if we'll manage to do this in the hour. Probably this episode will run a little bit longer, maybe quite a bit longer, but I actually do want to, like, just trace everything and to understand how everything fits together. So let's get started without any further ado and without any further tweaking of audio setup. Okay, so I definitely need my terminal, and we open Codebase, and we start from the beginning. We start from tinyBittle.zip. So tinyBittle.zip, a very important file that defines our data model. What tinyBittle is about. tinyBittle is about tracking financial transactions. So we are not a general purpose database which exposes some kind of a relational query language or just a raw key value store. No. tinyBittle exposes a single particular scheme which is hard-coded in the database, which is like not super flexible, but which allows us to run super fast. And that scheme is double entry accounting. There are just two entities in your database. There are accounts and there are transfers. So transfers, accounts. Accounts have balances, debits and credits. And transfer increases debits and credits of two corresponding accounts, maintaining the double entry bookkeeping invariant that the sum of all credits is equal to the sum of all debits across whole accounts. Now, why this particular scheme is what we're using is like outside of the scope of this topic. So this is like, this is about accounting rather about programming. But for us, as a database developers, the task is to make this scheme run really fast. And what is fascinating here, why this is a hard problem? The hard problem here is because each transfer touches two accounts. And this creates an obstacle for making this thing run fast in a straightforward way. Like, how do you make stuff run fast? Well, you just buy multiple CPUs, you buy multiple machines, and let each machine handle a specific shard, a specific subset of your incoming load. This, like the prerequisite for this kind of solution is that your workload should be able to be sharded. It should contain many independent parts. Now, because each transfer involves two accounts, it might be the case that any two transfers might actually conflict with each other. So, like, it's like one transfer adds to account and another transfer subtracts from this account. Like, you kind of like have to run this transfer on the same machine because you need to know like this account balance at a point in time. So that's kind of like, but well, like presumably you could maybe work around that by adding a bunch of locks here and there. So okay, suppose you add locks. Now we come to the second problem, which is inherent in this problem of tracking financial transactions. And that problem is not only each transfer touches two accounts, but also there is kind of like power law distribution of account popularity. Kind of like roughly, if you look at a set of transactions in any given like minute or hour or day, what you would see is that 80% of transactions touch one of the 20% of most popular accounts. So there are a few popular accounts which generate a lot of transactions. And even, like, within those like 20% most popular accounts, the 20% of that would be responsible for 80% of 80% of the transfers. So you have few very, very hot accounts. And if you add, if you try to shard this workload using some kind of logs, you'll notice that like popular accounts are popular. Like you can't really distribute the work across popular accounts. So that's why the big plan for Tagabital is to actually go in the opposite direction, to not even try to make this stuff parallel. And instead, like we say, okay, we're going to process everything on the single thread. We're just going to literally arrange all the incoming transfers into some linear sequence and process that sequence sequentially on a single core without any kinds of logs. And instead, the theory of performance is that we'll optimize everything else. So although the core of our system is sequential, it is like so fast that you actually don't need more CPUs. Okay, so let's see how this model actually gets executed by the cluster in such a way that the cluster behave as if it is a single machine. In particular, it provides strict serializability. You could generate a global order of all the transfers, which is consistent with the actual results in the database, and also executes the transactions in a durable way. So even if, like, some of your machine crashes, and even if some of your hard drives catch fire, or if even if some hard drives like not only catch fire, but just return outright bogus results, the system behaves as if nothing happened, as if the data is safe, well, because the data is safe. Okay, so this starts on the client, which makes a request. And what is the client? Here we come to another unusual fact about Tagabital. So the first thing is that, like, hey, this stuff is single-threaded. Like the zero thing is like, okay, we've actually covered like a bunch of interesting stuff already. Like, hey, this is in Zeek. Hey, this is single-threaded. Hey, this assumes disk false. But okay, the end interesting thing about Tagabital is that everything is batched. Like, we want to have only a single thread which processes transactions, and we want to run this very, very fast. One way to make this faster is to say, okay, instead of processing just a single transfer at a time and incurring some like coordination overhead for every specific transfer, we will be processing a batch of transfers at the same time. So, like, from the perspective of the logical model, yes, transfers are processed one by one. But from the perspective of physical model, how this actually executed, we are going to batch 8,000 transfers into a single message, which is going to be about 1 megabyte long, and we'll process this message as a single unit. So when the CPU gets to run the transfers, it will actually be immediately presented with 8,000 transfers and could potentially optimize the work and amortize some parts of the work for this entire batch. So this is why our client isn't actually going to submit a single request, a single transfer. It is going to submit a batch of transfers at the same time. And importantly, like, there aren't going to be like thousands or millions of clients. They're going to be like, I don't know, maybe like a dozen of clients which send those batches to Tagabital, because the actual clients in the entire API, in the entire architecture of the system, are going to be API gateways. So if people make payments using their phones, those phones make REST API calls to stateful API gateways. Like, there are like thousands of phones, but there are there is only a dozen of the gateway. Each gateway is going to run a targetable client internally. And a gateway will accumulate a batch of 8,000 transfers from a bunch of phones, and then send this individual, this whole batch as a single target level request to the target cluster. So this is the function which we are looking at, making a request, where the important things are the operation. So this is either create transfers or create accounts, and the events. Events is a slice of bytes, but actually, like, physically, this is essentially a slice of targetable transfers. We just don't care that this is transfers because we want to keep these polymorphic over the operation. Okay, so how do we send a request? Here we have to learn about message. In targetable, we think a lot about mechanical sympathy, and we think a lot about data-oriented design. So we kind of like think about the problem of solving transactions as a problem of data transformation. And to make this run fast, we actually want to avoid transforming data needlessly. We want to do as few data transformations as possible. Everything we do with the data, we want to be meaningful. And for this reason, we only have a few types which store something in targetable. So instead of, like, transforming data meaninglessly from form A to form B, we only do that where that makes, like, well, not where it makes sense, but where it is required by the shape of the problem. And in particular, that means that message type plays a very important role in targetable. So what is a message? Message is just a buffer of bytes of length 1 megabyte, which starts with the header, where the header struct is shared across all types of messages. And you'll see that this message is simultaneously what we receive from the network and what we write to disk in our journal. Like, if we were writing some kind of abstractions, then we would have an abstraction for network and then an abstraction for disk. And we'd actually, like, edit encapsulation to make sure that the data representation on the network layer doesn't affect data representation on the hard drive. And that would be a good solution if we would like to optimize the ease of change between network and hard drive, but it would be a poor approach if what we actually cared is performance. Because if you, like, if you do data transformation, then you spend needless CPU cycles. So for us, the answer is like, no, we actually aren't going to add an abstraction there. What we get from the network is exactly what we are writing to disk, and this is just a single message type. Okay, so let's see how we feel this header, what we do with the message. So first of all, we acquire a message from a message pool. And again, kind of like small detail. From the message pass, well, I actually acquired from the message pool. Get, do we have, okay, let's see. in the message bus, we have get message, and that calls to pool get message. Okay, yeah, that is the thing. So one of properties of Target is that Target doesn't do dynamic memory allocation. That is just to make the system more reliable. Like, you know, if you don't allocate stuff, then stuff doesn't break due to out-of-memory errors. Moreover, if you don't allocate, that like forces you into knowing all the actual limits of your database, and that in turn forces you to be like very cognizant about like the actual resources you need to run the system. So like, you know, you don't just hope that you'll give it enough stuff. You actually get to know exactly how much stuff do you need. And for messages, we'll see that we just compute the static limit for how many messages do we need, and then when we initialize this thing, yeah, we just go and allocate exactly that amount of messages. I guess it would be good to say like, how do we compute the number of messages? And that's actually pretty easy. So there is like only like certain amount of clients connecting to a cluster. And there is only a certain amount of replicas in the cluster. And there is like bidirectional connections between all of them. So, you know, there is like for each thing which could talk to the current replica, there is like an incoming buffer and an outgoing buffer with like of some length which holds messages. So essentially, you just take the length of those buffers, you multiply that by the number of peers you're talking to, and that is your limit for the number of messages. Okay, so for the client, we get a message. We filled the header fields. I guess the most important thing here is like this command, which says like, hey, this is the request from a client, and this client ID field, which says like, hey, which client it is. Then we copy the actual transfers events into the message, and then we go and fire up the request, where firing up a request means just writing it over TCP to the replica through our message bus abstraction. So we go to send to the replica, and then we go message bus send to the replica. So now message bus. Message bus message bus. Message bus is our abstraction over TCP. So we don't like, you know, we want Target to be transport layer agnostic. So we want to be able to run it over like raw TCP, over TLS. Maybe we at some day would like to run it over QUIC or raw UDP or whatever. So we don't actually expose like raw streaming abstractions to the replica, and rather it all goes through the message bus abstraction, which can send and receive messages. Not like, you know, like abstract message, but that very concrete message which we have just seen in the message pool. That message which is just a megabyte of data. So I guess we won't go into how client actually establishes connection to the replica, but that's like at this point is pretty easy. We just require that replicas know each other IP addresses and clients know IP addresses of the replicas. So the client just like goes and deals in. So we have like as a result of that, we maintain a bunch of TCP connections for each replicas. And when we need to send a message to a replica, we pick connection, and we send the data down the pipe. Important thing, this is distributed system. So even if we send our message, there is no guarantee that the replica will receive it. which is kind of like bad because that means that we need to deal with it. That means that we, in the client code, we need to have some kind of timeouts. So if you see, yeah, we have this like request timeout, and like in the client code on request timeout, if we have a request in flight, then we're like, no, go and retry this request. So this is kind of like extra complexity. But there is a positive side to this constraint that, hey, network actually is laggy and it might drop messages, is that if errors can happen, and if there are retries and there are retries outside anyway, we could actually massively simplify error handling, because like, if there is an error and you for some reason cannot like fulfill the operation, well, it's not a problem, you just do nothing and wait for the retry. And this is exactly what this send message to replica function does. So if we have a connection to replica, we send it a message. But if we don't have connection to replica, well, like, never mind, we just drop a message, and at some point later the client is going to retransmit the message, and it will eventually get through. Comments from the chat. With the use of TCP and clients only having one in-flight request, any packet loss could have a big perf impact. So I guess it might not necessarily be true, because again, because we're using TCP, if you lose a single IP packet, well, that packet is going to get retransmitted by the underlying TCP implementation. So actually, here, like again, like the optimal implementation would use UDP and like implement its own congestion control. We don't do this. We do rely on TCP to do this like fine-grained retransmit. But overall, like, yeah, I'm not like right now, I'm not claiming that the code here is like the optimal way to get networking perfectly optimal. Like again, this is actually okay. This is very important point. Very important point. Tagametal is a new code base. We have a production release, but our production release is less than a year old. So we are very confident in what we ship today, and we are very confident that the architecture we use is going to scale to like unimaginable performance. Like really, all the right parts, all the ingredients are there. But we definitely didn't do all the work to actually go and optimize this code. And well, that's what we're going to be doing like for the next like 10 years or so. Actually like unlocking all those performance benefits which are made possible by our architecture. So it is totally possible that in the code we are looking at today, there is like some kind of like, horrible performance bug where like a single dropped network packet might cause a latency spike. We aren't at the place where we can guarantee that, hey, we kind of like solved all these problems. But the big picture should be pretty fine. Okay. So anyway, if we have connection to the replica, we send this replica a message. And sending a message means that we push the message to the outbound queue for this connection. Again, this is the queue which is one of the main ingredients which determines how many messages we actually could have in flight at the same time. And again, if the queue happens to be full, like no problem, we just drop this message on the floor and rely on retransmit. And then we actually go and send the first message in the queue. So how does the send works? Well, this is the actual syscall, the actual send, or, well, it could have been write, but well, we use send, syscall to the kernel. We submit our syscalls through IO URING, so it is completion-based asynchronous interface. So that's why kind of like the way this looks from outside is that we say, okay, please, dear kernel, This is the part of the buffer we want to send. This is the file descriptor we want to send, and please arrange for this to be sent through your TCP implementation. And when you're done, call on send function. So we fire this up to the kernel. The kernel then returns with the result. If the result is some error, not a problem. We terminate connection. We don't report error anywhere. We just drop all the messages which were queued up on this connection, because again, there is a retry loop on top of it, so we don't have to worry about error handling. Otherwise, well, we kind of we were able to send at least some part of the buffer. So we increment the counter, which says how many bytes we have sent, how many bytes there are left. If it so happened that we've sent the entirety of the message, which is currently the hand of a send queue, we pop this message and drop it. And then we kind of either continue sending this message if a single syscall wasn't enough to do all of it, or otherwise we pop off the next message from the queue. Okay, so this is requests. So we have a bunch of transfers. We pack all those transfers in a single buffer, which is a wide megabyte long, which adds up to about 8,000 transfers. And then we send this whole pack to the cluster. Specifically, we send it to the primary. So what happens next? This is replica. This is the code which actually runs on one of the 6 members of the cluster. And well, yeah, before we get to the replica, let's actually go back to the message bus. So we right now we've seen the client side of the message bus, how we send messages. There is the opposite side, which receives messages, which is implemented in exactly this function. And this is, I think, this is receive. Again, replicas and clients establish TCP connections. Replica plays the role of the server, so periodically it calls receive on the corresponding file descriptor. So we say to the kernel, hey, dear kernel, please, this is the buffer for you. Try to receive some TCP bytes there. When we receive some bytes, again, if there is some error, we just tear everything up. Well, no, we tear everything down. We don't report this error anyway, we just log it, and then we restart everything. Because, again, there is end-to-end retransmit. So we don't have to worry about handling every individual error. Okay, so we kind of record that, hey, we now have this many bytes received from the network. And now, if it happened that we received some number of messages, we actually go and process the messages. It's interesting how we do this. So remember that every message starts with header. So the first thing we check is that we have at least a size of header bytes received. If that's not the case, well, we just go and repeat our receive syscall until we get enough stuff on this connection. Otherwise, we go and validate this header, and this is pretty important and pretty cool. So you see, message starts with a header, and the header carries checksum of the message, but actually it carries 2 distinct checksums. It carries the checksum which covers just the header, and then separately it carries a checksum which covers the entire body but excludes the header. And importantly, this second checksum is protected by the first checksum. So when we compute header checksum, we actually compute checksum only over these fields. Actually, yeah, let's just how it is called, set checksum. Yeah. So I'll just like see how calculate checksum works. Okay, this is the header. We know that the checksum is the first field in the header, so we subtract this first 16 bytes, compute the checksum of the remainder, and then we set the checksum. And for computing the checksum of the body, well, we kind of like just compute the checksum of the body. And we store that in the checksum body field. But because the checksum body field goes after the checksum, it is actually covered by the checksum. What also is covered by the checksum is this size field. So actually, let's go back to the client to better see this. Okay, so we set the size here, and where do we set the checksum? Okay, yeah, so here we also set request number. But where do we actually set the checksum? Okay, yeah, here. So okay, so apparently we don't set all the fields of a request in the request. There is like some extra things, but this is like important that we first set the checksum of the body, and then we set the checksum of the header. That way, checksum of the body gets protected by the checksum of the header, and importantly, the size field also gets protected by the checksum. So going back to message bus, when we receive a message and parse the header, if the checksum is invalid, we immediately shut down the whole thing. Well, not the whole thing, just like this connection. If the checksum is valid, we actually know that the size is also valid. So once we know the checksum, we could go and proceed receiving that many bytes to get the body. And this is important because suppose we actually didn't cover, like, this size field by the checksum. And that could mean that the size field could get corrupted during the transfer. And like, let's say you receive a message and it says like here, like my size is like 5 gigabytes. And then you like, receive 5 gigabytes of a network, and then you like compute the checksum of those 5 gigabytes. And then like you realize that here actually like the checksum is much. So something was wrong, and potentially the size field was wrong. So this, like, having two checksums protects you from having these kinds of framing errors. So anyway, we validate the checksum. If we haven't received the data for the entire body, well, we need to receive some more data. And if we did receive enough data, we copy this into a separate message, and then we return this message, which will call a callback on. So this goes like, now we can go to replica, and we could go to replica's own message from bus method, which is exactly what message bus calls when it receives a message which has valid header checksum and valid body checksum. Okay. There's like some type shenanigans, and we like handle all kinds of messages based on the command field in the header. This command is exactly what determines which prong of this switch we are going to take. And what we get from the client is the request, which I can't actually even find here. Okay, request start. Okay, yeah. Okay, my cursor was redundant. Okay, so what happens with the client request? And here we need to talk a little bit about consensus. So, what is consensus? Kind of the goal of consensus is to take a cluster of 6 machines and make them behave as if they are just a single machine. So why do you need consensus? Why, why 6 machines together are not exactly as a single machine? Well, there's 2 reasons for that. One is that, machines might have different data. So if you send X to machine A, and then you send Y to machine B, then A has X and B has Y, but they kind of disagree. They don't have X, Y. So one job of consensus is to propagate the data across the cluster to make sure that if machine A receives X and machine B receives Y, then they send it to each other and they both get X, Y. So that is the first thing, just getting the set of data to be shared across machines. But then there is a second problem. Suppose that machine A receives X and then Y, and machine B receives Y and then X. And at this situation, it's kind of well, it might be for some X and Y, it might actually not really matter what order they were received in. If for example, X and Y are things like, hey, add this to the set, or increment the counter. If you increment by X and increment by Y, or increment by Y and increment by X, that's commutative, so you don't matter, doesn't matter for you. But for us, given that we are doing financial transactions, given that we are doing transfers, it is very much matters in which order transfers are processed. Because if you have 2 transfers, you might have money only for one of them to succeed in your account. And it is important that it's that everyone agrees on which transfers succeeded and which transfers failed. So that is the second job of consensus, making sure that everyone in the cluster agrees on the order of the events. And this is the first thing which will happen with the incoming request. We will convert it from the request to the prepare. And here we probably need to take a closer look at the data in a single request. So let me maybe drop, I can just fold comments so we could see it clearly. So this is request. And this is prepare. Okay, so there's a bunch of common fields and a bunch of different things. And the crucial difference we are interested in is this op field. So you see, it kind of similar to this request. So both request and ops are sequence numbers. And the difference here is that request is a sequence number which is local to a particular client. So when a client sends a request, for its first request, it sets request 1. For the second request, it sets it to 2, then to 3, etc., etc. But this doesn't really allow you to order requests across the clients. In contrast, this op field is global and unique for the entire cluster. So each request gets converted into the prepare, and a prepare gets assigned an op number. And all those op numbers are unique across all the prepares. And this act of assigning an op number is exactly that part of consensus which ensures a consistent ordering. So going back to our own message inside replica, we are handling request. And our primary goal and this is an intentional pun, is to convert a request into a prepare by assigning it an op number. Now, how can you assign consistent incrementing op numbers in a cluster of machines? And that's very simple. You have a single dedicated machine which is called the primary, and you only let the primary to assign op numbers. So in effect, if a machine receives a request and it is not a primary, it sends this request to the primary, and if machine which received the request is a primary, it sends op number and increments its local op. Now the question is like, what happens with the primary crashes? Well, then you need to elect some other machine to be a primary, but then the question is like, hey, what if the primary didn't actually crash and was just slow? Now you have like two primaries in the cluster. Well, and that is like, that is like the whole consensus algorithm determining which replicas are actually the primary. Well, okay, maybe, okay, yeah, I promise to cover everything, so we'll cover bits of it today as well. But for now, let's ignore this. Okay, so we received message. What do we do? First we check whether we need to ignore this message. For example, if we have already received this message, or if we don't know about this client, or stuff like that. But importantly, we have like this case that, hey, if we receive a message and we aren't actually a primary, then we go and forward this request to the primary. Okay, so we only get here if we are in fact the primary. Okay, now, primary can process only so many requests at a time. So if primary's prepare queue is full, we just queue up this request for future processing. And if we actually have some space to process this prepare, if we have some space for a new prepare, we go and convert this request into prepare immediately. Now, what is prepare processing? That is more. That is two things. First, consensus, to actually double check that, hey, you are indeed the primary who is allowed to prepare prepares, and then it's actual execution. So going and running all the transfers inside this prepare. Okay, it's 51 minutes and we have just started. Okay, I feel like this could go for quite long. So brace yourself and prepare for a long episode. Okay. Primary pipeline prepare. So we have a request. We want to convert it to prepare. And this is some special casing for some built-in operations. Then we have state machine prepare, which actually doesn't do much useful. Then we have timestamp handling, and for time, I guess let's keep it out of scope for today. But the important thing here, yeah. So we convert this message to a prepare, and we literally do this by overriding the header message. Incrementing this op number. So you see this op number is replica local primary local state, which says which op number is next. So here we set the header's op as self op +1, and then we actually process this message as prepare, and as a side effect of that, we expect our local op to be incremented. Question from the chat. Do clients try to connect to the primary, or are they happy to connect to any node? Yes, clients try to connect to the primary, and there is a protocol which basically gossips to the client which node is currently the primary. But if the client sends message to some node other than the primary, it still works. This is also like not something which is like fully finished yet. So we have some code which makes cluster partially available for you if you could talk to some node but cannot talk to the primary, but this is like rather ad hoc at the moment and isn't really like fully completed. The end game here is, yeah, totally, like if you could talk to any node in the cluster, then you should be able to send requests to this cluster. Okay, so as a primary, we convert this request to prepare, and now we process this prepare. Now, the two important calls in this onPrepare is this replicate message part and append part. Okay, so let's quickly talk through part of the consensus protocol, the happy path, which is actually just replication and which is quite fast. So, okay, we are a cluster of 6 nodes, and our task is to pretend that we are just a single machine. The idea here is that for everything that you do, like, on behalf of the cluster, you need to make sure that this is done by a certain quorum of machines. So if you say that, hey, the thing happened if it happened on the majority of machines, then kind of like, if some parts of the machines then fail, then you could still trace back that, hey, that thing actually did happen. So for us, for Tagemitl, that means that to consider prepare committed, this prepare must be replicated to half of the cluster. So for the cluster of 6 nodes, we require that the prepare is replicated to at least 3 nodes before we can act on it. Why 3? Why not 4? Well, like in like traditional consensus algorithms, you need majority of the nodes to agree on something. But there is like a cute trick where you could speed up replication at the cost of making leader election or view change slightly slower. And this is usually a good trade-off to make because replication is actually the hot path. Basically, you could replicate to 3 out of 6 replicas, but then you require that 4 replicas participate in a view change. That means that among the replicas participating in the view change, for every committed prepare, someone knows about it, even if the prepare was replicated only to half of the cluster, not the majority. Okay, so replicate is actually relatively straightforward function. We essentially, if we are like replica n, then we go and send this message to the replica n+1. And that's it. So replication is ring-based. We want to avoid a situation where the primary just broadcasts message to everyone, because that means that the primary needs to have 3 times as much bandwidth as everyone else, or like even if you broadcast to 3 things. So that's why we like doing just the ring replication. Of course, this could break if you break a single link in the string. And that's why we have on top of this a retry loop, which would try to broadcast this message to a random replica if we realize that we haven't received enough acknowledgements about this message. Okay, so this is replicate. The second thing we do is that we append the message to our write head log. Again, this is consensus, this is distributed system. So one of the failures you have to deal with is your node crashing. If you crash and you restart, you need to be able to not lose data. And that actually kind of like, solidifies the meaning of this replication thing. So what does it mean to replicate a message across across 3 peers? It doesn't mean that you just like send message to 3 other nodes in the cluster. No, it means that you send those messages, then each of the recipients received the message fully, has written it to disk, and replied to you. So you could only acknowledge receiving of a message if you actually appended it to your local write ahead log. And this is what we do here. So we call write prepare, and that internally calls journal write prepare, which is maybe a little bit too complicated for us to look in deeply today, but I still want to cover a little bit of it. Okay, so let's see how we write prepare. So this is our message, and then we take only the header of our message, and we write only the headers. So we call write, passing these headers and passing this callback. And once okay, this doesn't make sense because I was assuming we do this actually in the opposite order. Maybe, well, let me quickly okay, yeah, sorry, I get confused myself. Like, no, we are not writing just the headers immediately. We actually do write the entire message. So, like, the buffer is like always statically allocated to be 1 megabyte. The message might be shorter than that. So we slice the buffer and ask the journal to write that prepare. But afterwards, what we do is that we schedule a second write. So this time, we only write message headers. Okay, let me check. And here we actually don't use just message header. We use our in-memory sectors. Okay, where we do this. Okay, let's see where we set this prepare, where we set this here. Right, prepare. Okay, yeah, here. So after we have written prepare, we save just the header of this prepare into this headers redundant, and then we write parts of those header redundant. So I think, oh, maybe I'm wrong. Okay. So where do we set this header? Oops. Okay, so I'm a bit lost in the code, and I don't want to waste too much time on that. But basically, the idea here is that when we append prepare to the journal, we obviously write is prepare to the journal. But what is not obvious is that we also write a separate copy of just the header. So for every prepare we want to journal, we actually journal it twice, as a full prepare, like 1 megabyte, and then as a header, just 256 bytes. So why do we need to do this? Well, this is required to figure out where a particular write is stored due to the replica crashing. So imagine you're a replica and you're writing a prepare. And while you are writing a prepare, suddenly the power goes down, or maybe something else happens, like I don't know, like your kernel crashes or whatever. Then that disk write, which was writing the prepare, obviously doesn't finish, and it might be like a single physical disk write. It might be like many logical disk writes. Actually, let's quickly look at here. So the underlined writing function is write sectors, which calls storage write sectors, and this function writes this entire buffer into a specific offset in the data file. And internally, you see that it can result in multiple write syscalls to the underlying storage. So we try to write our buffer, and if we written the entire buffer, then we are done. But if we have written, we did only partial write, then, well, we go and start writing again. So yeah, and if, in the middle of this thing, your replica crashes, well, then writes won't be done, and you'll see some garbage on the disk. Now, how do you determine that you have some garbage on the disk? Well, you restart, and then you read your journal, and you verify the checksums of all the prepares. And if for a single prepare the checksum mismatches, then it is garbage. And one reason for why this prepare is garbage is that this is exactly what happened. You were writing this prepare to disk, and then you crashed. And that means that because you were writing this prepare, you haven't actually acknowledged it to any other replica in the cluster. So in this case, it would actually be safe for you to truncate this prepare, to pretend that you have never received it. And this is what most databases do. Unfortunately, if the checksum doesn't match, this does not necessarily mean that this is indeed a torn write. Because, well, disks are unreliable. They are especially unreliable at scale. Like, a single individual disk in your laptop might very well last for your laptop's lifetime pretty much fine. But if you have like many clusters with many hard drives which are heavily used, there are bound to be some errors. And a latent sector error would manifest exactly as an invalid checksum. And if in that situation you actually go and truncate this prepare from your log, you like pretend that you have not received it, you might violate durability of the entire cluster. Because, so this is what happens. Before the crash, you receive a prepare, you write it to disk, you communicate to your peers that, hey, I now have this prepare. And the cluster acts under the assumption that the prepare is actually replicated. And then say, you crash, you restart, and there is also a failure on disk. So after restarting, you find this prepare to be corrupted, and you act as if you haven't received it. If at this moment view change happens, if the cluster transitions to a new primary, that new primary might consider this prepare to not be replicated in the cluster and might actually, drop it from the history of the cluster, which would be a data loss. So some clients would consider the transfers in this prepare as successful, but other clients would consider them to be failures. To solve this problem, we do write an additional persist record. So first we write prepare, and then we write header. And now, if you start up and your prepare is corrupted, but the redundant header is valid, and it is a header for some old prepare, then you know that, hey, this indeed was crashed and the torn write. Because you write and prepare, you were partially through write and prepare, you haven't fully written the header. Replica crashed. Okay, this is clearly safe to truncate. On the other hand, if you get a latent sector error, if you get like random corruption, then what you'll see is, hey, my prepare is corrupted, but my header is actually intact. And my header says that, hey, I should have had this prepare. So in this case, you as a replica, you realize that, hey, actually, it's not going to be safe to truncate this prepare. It's not like you should not advertise as if you don't know about this prepare. Of course, it could be the case that, disk corrupts both the header and the prepare, or disk corrupts just the header. And yeah, kind of like in some of these cases, the replica would wrongly claim that it kind of gets corruption. But the important thing is it's okay, so I guess I'm talking nonsense here. So let me try again. So of course, you cannot protect from all the disk errors. For example, if a failure mode of your disk is that your disk is dev null or some TMPFS thing, if you write to it and then you crash and you restart and the disk looks as if it is completely pristine, then of course you're going to lose data. So we we do require that the disk at least tries to store data. And we require that if you write a prepare and then write a header, then at least one of those to write survives. And if both are lost in the midst of time, then yeah, you do get a data loss. But we do recover from any single disk failure, and we recover from many instances of multiple disk failures. Okay, so that was appended the prepare. On prepare. Okay, so we as a primary, we replicated the prepare and we appended it. And by the way, this same thing happens on the backup as well. So this function on prepare works for a primary and works for a backup. They both like replicate in the ring topology and append to the journal. Once, okay, let's zoom into this append function. Once we appended a prepare, well, we do write prepare, and then again, this is asynchronous function, so we pass prepare to the journal and we pass a callback. Then the callback returns. When the callback returns, we send so-called prepare OK message to the primary. So what is prepare OK? Well, prepare OK is basically a message which says, hey, I have appended this prepare to my local disk. So you could count me as a part of replication quorum. Just a second, I need to answer my phone. Okay, so I was actually going to make this a super long episode, but well, likely for you, something has just come up, so I will wrap it at this point, and we'll continue with our overview next time in exactly 1 week at 5 p.m. UTC, live on Twitch and on YouTube in recording as well. Okay, I'm actually satisfied. It was really really great cliffhanger. Like you just talk, and then like in the middle you just get it off, because well, now you absolutely have to watch the next episode as well, the Grand Recap Part 2. Okay, so thanks for joining today, folks, and see you in 1 week. And I'm going to put out some fires. Thank you.